Okay, so we have an electrically neutral linear polar molecule has a positive charge equivalent to charge on one proton centered at 0.30 nanometers from the center mass, and equal quantity of negative charge centered at 0.10 or a tenth of a nanometer from the center mass. So opposite of the positive charge. And it was given that the electric field is 100 newtons per coulomb. So in this problem, it asks us to find the torque max and the torque minimum of the molecule. And so because this has a proton and a neutron, I think of P equals QD, which P is for dipole. So then, knowing that the charge of a proton and electron are 1.602 times 10 to the negative 19 coulombs, I might have rounded that a little bit. And then the distance, which stands for D, is going to be 0.3 times 10 to the negative 9 because we're dealing with nanometers. But we also have the 0.10 times 10 to the negative 9 meters as well. And so that's going to get us our dipole. I need to use my calculator. Oh boy, I should have been prepared. So let me plug that in. And so we have 1.602 times 10 to the negative 19, and we're going to times that by the length. 0.10 times 10 to the negative 9. So meters. Okay, so what I'm getting as the answer is 6.408 times 10 to the negative 29, which makes sense. 29. Yep. Okay. So that is what I'm getting. Oh, by the way, let's make sure we do our units. So it's going to be coulombs, coulombs times meters. And so that is our dipole. And so the torque is going to be the dipole times the electric field, and then because we're dealing with the torque, so it's a linear, so we have our dipole here, and so we're going to want to be looking for sign, like the y direction, between the two, because that's what you do. It's torque. Is parallel. That's the word. We want it to be parallel. And so it's sine. And so then from that, so the maximum, would be straight up, right? That'd be 90 degrees. Whereas the minimum torque on this dipole would be the opposite, negative 90 degrees. So for T max, we're going to take the dipole 6.408 times 10 to the negative 29 coulomb meters, and then we're going to times that by 100, and then we need to take the sine of it because it's torque. And so let me do that really quick. And then what I'm getting, and this would be the maximum torque possible, would be 6.408 times 10 to the negative 27. And that's going to be, the coulombs are going to cancel out, leaving you with Newton meters, which that makes sense for torque. So that is for our max. Now we want to find our minimum. So we're going to take, again, proton, electron, same, that charge, because it's a dipole. So we're taking the dipole, and we're going to, electric field is uniform throughout. Oop, that's a C. And then sine negative 90. Okay, so we do that. And we get the negative of the above number. So it's negative 6.408 times 10 to the negative 27 Newton meters. And so from this, we are taking two molecules, which end up making a dipole, and we are taking the distance into consideration because we're going to use the dipole equation so that we can find the dipole, and then take that dipole and find the torque on it, which would maximum torque would be 90 degrees, and then your minimum torque on it would be negative 90 degrees. So you find your dipole, and then you multiply it by your electric fields, and you have to take the angle in between, so sine 90 and then sine negative 90 for the minimum. And so there you go.